Okay, so we're going to look at inflammation. So I want to start with just the normal physiology, and then we're going to look at what happens with inflammation, and then we're going to take it from a localized inflammatory response to a systemic inflammatory response. So the situation right now is we have this individual, and right now everything's fine. They've just got the normal physiology going on right now. So this is a blood vessel right here. These are endothelial cells. This is a vascular smooth muscle. We look at connective tissue proper. In connective tissue proper, we have things like mast cells, macrophages, fibroblasts, peripheral dendritic cells, and so everything's normal right now. We've got blood flowing this direction. In the blood vessel, we have neutrophils. Okay, neutrophils are being pushed along by hydrostatic pressure of the capillary. As we go from one side to the other, we have hydrostatic forces within the capillary. And these hydrostatic pressures of the capillary are pushing fluid out into this tissue area. However, we also have oncotic pressures of the capillary. And the oncotic pressures of the capillary are pulling fluid back in. So we're pushing out on the arterial side, pulling back in on the venous side. If we do happen to leave fluid out here, it's going to be picked up by the lymphatic system. Now what we're going to do is we're going to induce injury. We're going to introduce a pathogen into this situation. So let's say that this person gets a splinter in their finger. So we're going to just look at this localized response right there. Now, a localized response is actually a good thing. You want an acute inflammatory response if you have a localized insult. So we're going to take this individual, we're going to introduce a pathogen on this splinter. So here's this pathogen. Now, the pathogen is going to produce, just as a byproduct, it has metabolic byproducts, and it also has things, proteins in its cell wall, peptidoglycans. If it's gram-negative, it could have things like lipopolysaccharides. But what this pathogen will do is it'll alert the immune response to itself. So here's what happens. The pathogen is going to, through chemotactic signaling, it's going to activate the mast cell, and it's also going to activate my macrophage. The macrophage has things like TLR4s that would be, that if this was gram-negative, it would produce the lipopolysaccharide. The lipopolysaccharide would plug into the TLR4, and then in response, it's going to release these monokines, these cytokines in response to the activation. On activation of the mast cell is going to go ahead and degranulate, and it's going to release histamine. Now, histamine is going to start this process going. Because here's what I want. I want to get this neutrophil out here, okay? Because I want to get this neutrophil to confront this pathogen. Right now, hydrostatic pressure is pushing this neutrophil along, and it can't exit the vascular system. One is because the selectin ligand that it has right here, so S-SLIG stands for selectin ligand, there's nothing complementary to it to interact with. In fact, its complementary molecule that it can actually bind with and tether with is actually inside the endothelial cell right here. And so inside the endothelial cell, we have what's called this P-SLIG. Okay, so you have P-SLIG or E-SLIG, which is platelet selectin, or also endothelial selectin. But it's inside here. Right now, it can't have access. But we're going to show how this process works, that it will be expressed. So histamine, it's going to be released, and it's going to plug into my H1 receptors. So I have H1 receptors on endothelial cells. When histamine plugs into these receptors, it allows calcium to come in. Now the entry of calcium into, or the introduction of calcium in here is going to do this. Here's my calcium that's outside. It comes into the cell, and when it does, it allows for contraction of these endothelial cells. It causes the cytoskeletal elements within them to contract away from each other, and now I've increased the size of my intercellular cleft. As I increase the size of my intercellular cleft, I've done two things. One is I've allowed a pathway by which the neutrophil can exit the vascular system to go out into this extravascular space. But the other consequence of this is I'm leaking protein. The protein that was producing my oncotic pressure is actually starting to leak out here. So the consequence of that is I'm increasing the oncotic pressure of the interstitial fluid while dropping the oncotic pressure of the capillary. So I'm pulling more fluid out and pulling less fluid in. Now, there's another thing that happens when calcium enters into the cell. Calcium will stimulate the synthesis of nitric oxide through the activation of INOS, inducible nitric oxide synthase. Inducible nitric oxide synthase will diffuse over into the cell, the vascular smooth muscle cell, and it'll increase cyclic GMP. Now, you may remember from physiology that an increase in cyclic GMP will actually cause vasodilation. Because under normal circumstances, I have norepinephrine being released, and the norepinephrine is plugging into the alpha-1 receptor, activating a GQ protein. That's activating phospholipase C. Phospholipase C activates IP3. IP3 goes to the sarcoplasmic reticulum, and it allows calcium release. That calcium release allows calcium to bind calmodulin. The calcium calmodulin complex allows the activation of myosin light chain kinase. Myosin light chain kinase splits ATP into ADP. It takes the phosphate from that reaction, and I take my myosin, I add the phosphate derived from the ATP, and I get contraction. So right now, norepinephrine is causing the contraction. Cyclic GMP comes in there, and cyclic GMP activates a myosin light chain phosphatase. Myosin light chain phosphatase removes the phosphate from the myosin. It also inactivates myosin light chain kinase, so I don't produce new phosphate for the myosin. So this is a very efficient, the increase in cyclic GMP under the influence of nitric oxide that was produced from the activation of INOS, is very efficient at causing vasodilation. And that's fine, because I want vasodilation in this area because it's a localized area. So now if we just kind of look and see, where we're at on inflammation. Inflammation results in four main things. And so if you remember from your physiology, one of the things it would do is it would cause redness. Well, why did it cause redness? Well, the reason it caused redness is because of the nitric oxide. Nitric oxide vasodilated these vessels, and so superficially, I've got vasodilation of these superficial vessels, and that's causing the redness. It caused heat. Why heat? Well, the area feels warm because one reason is that temperature, body temperature is about 37 degrees Celsius, or 98.6, but the temperature of blood is about 104 degrees. And so since blood is warmer than tissue, the more blood I have circulating in this area, the more heat I'm bringing to this area. Another thing I see is edema. So why edema? Well, edema is happening because of a number of reasons. One is when I vasodilate, I get more flow in here, and I increase the hydrostatic pressure of the capillary. The other thing, so I've increased the hydrostatic pressure of the capillary. Another thing I've done is the endothelial separation, where I increase permeability under the influence of histamine. I lost oncotic pressure in the intravascular space, so that oncotic pressure decreased, and then that protein went out here and increased the oncotic pressure of the interstitial fluid. So you can see now that I've got three things that are causing this increase in edema. And then, of course, the last thing is pain. And pain is occurring for a number of reasons, but you've got chemical stimulation of these free dendritic nerve endings because of some of the signaling that's taking place in here, but also just the swelling, this mechanical pressure on these free dendritic nerve endings. So we said that this is actually a good thing. And the reason it's a good thing is because my increase in hydrostatic pressure has allowed more neutrophils to move into this area, and the separation of the endothelial cells, or my vasodilation, which has increased the hydrostatic pressure, has allowed more neutrophils to move in this area. And then also the separation of the endothelial cells will now allow the neutrophils to move out into tissue. But the other thing is, when I look at the oncotic pressure, some of this is derived from complement proteins. If you remember from your immunology, undergraduate immunology, is that complement proteins can activate a complex called C3. C3 can form C3b, which can act as a C5 convertase and convert C5, which converts 6, 7, 8, and 9 into what's called the membrane attack complex. And the membrane attack complex can directly kill cells by lysing the cells. So it's not a bad thing to get the protein out here, because you are getting complement proteins into the area. So let's look at activation of the macrophage. So we activated the TLR4. Now, in response to TLR4, our activation, our macrophage is going to produce a thing called TNF. TNF-alpha. TNF-alpha is very significant because TNF-alpha will allow for the expression of this P-selectin molecule. So TNF-alpha will come over here, and under the influence of TNF-alpha, I can express my P-selectin. Now, P-selectin again is just P stands for platelet. I also have E-selectin, which is going to stimulate the synthesis of, and so I have E-selectin and P-selectin. But here's the main thing: is once my selectin ligand is activated by P-selectin, it tethers it, because hydrostatic pressure was pushing this neutrophil along, and it couldn't grab a hold. And it couldn't grab a hold because of things like prostacyclin being secreted. So now it can tether. That slows it down and it starts to roll. But as it's tethering and rolling, it's activating its beta-2 integrin. And so these beta-2 integrins, what they're going to do is they're going to allow for adherence onto the surface of the endothelial cell. So now I'm going to move my hydrostatic pressure right here. Now what I can do is I can actually marginate. So I've activated my integrin. That is going to allow the neutrophil now to form a tighter bond. So the integrin is actually going to bind to the intercellular adhesion molecule, the ICAM. Now I have this activated neutrophil. And it was because of the P-selectin interaction, the activation of the beta-2 integrin, and now the beta-2 integrin grabbing hold of the ICAM. The neutrophil now is activated. It's a killing machine at this point, because once it's activated, it's going to start to pull in oxygen from the plasma. And the reason it's doing that is because it's starting to increase its synthesis of oxidizing agents, superoxide free radicals, and also hydrogen peroxide, which is stored within the perioxysomes. It's going to be crawling along here looking for a way to get out. And thankfully, histamine has created that way. So now I can move out of here. The endothelial cells will create a chemokine, or express a chemokine called IL-8, and IL-8 tells the neutrophil, hey, move out here. So now the neutrophil will move along, and now it exits, it comes out here, and the neutrophil will now encounter the pathogen. Once it encounters a pathogen, it's going to form the phagosome. And by the way, this is not to scale, because I can fit within the body of a neutrophil anywhere from 5,000 to 18,000 white blood cells, depending on the size of the neutrophil and the size of the pathogen. However, the neutrophil is only going to eat about 8 to 18 bacteria, and then it's going to undergo what's called the respiratory burst. The respiratory burst releases these oxidizing enzymes and also superoxide free radicals from its lysosome, so it contains that hydrogen peroxide, and so it causes oxidative killing. But then it also, because it kills itself, it releases the contents of its lysosomes, and the lysosomes contain hydrolytic and proteolytic enzymes which start to break down the pathogen. So it just keeps spilling out and just killing pathogens, but also killing itself. That's fine. The macrophage, it'll clean up the mess, because the macrophage will come in here and clean up the mess, and then it'll become an antigen-presenting cell, which then activates the third line of defense. So the whole system, the way that it's designed, is to actually create an inflammatory response that responds to these localized invasive agents. And so that's when it's systemic. But what about when it becomes, that's when it's local. But what about when it becomes systemic? Because when it becomes systemic, all of a sudden we have a situation where this patient is crashing. Because think about this. Let's say that the pathogen wasn't here. The pathogen was in here. And the pathogen, instead of releasing the lipopolysaccharide into the tissue, it's releasing it into the blood. So when we look at sepsis, the majority of sepsis cases, almost 40%, are because of a gram-negative bacteria. That gram-negative bacteria is producing lipopolysaccharide. The lipopolysaccharide is being released into the vascular space, and it's activating the macrophage. The macrophage is releasing TNF. So instead of TNF causing the expression of P-selectin in this little area right here, it happens throughout the body. And now that it's happening throughout the body, our neutrophils are becoming activated. And as the neutrophils become activated, they're really not for sure where to go, because I'm not necessarily expressing my chemokine IL-8 that causes them to leave the vessel. So now inside the vessel, I'm activating these neutrophils. And as I activate the neutrophils, if they don't know where to go, sometimes they can undergo the oxidative burst within the cell or within the vascular space. I'm going to back up just a minute, because since this is happening throughout the body, my intravascular volume is leaving. And so my blood pressures are crashing. I'm becoming severely hypotensive, because all through the body I'm losing my oncotic pressures and they're moving out into the extravascular space. So my pressures are crashing. The other thing that's happening is I can start to form what's called DIC, disseminated intravascular coagulation. The reason that's occurring is because if the neutrophil damages the endothelial cell, so let's put a neutrophil over here and have it damage the endothelial cell and see what happens. When I damage the endothelial cell, I expose the subendothelial layer. The subendothelial layer is thrombogenic. It has what's called von Willebrand's factor. And this von Willebrand's factor, what it's going to do is it's going to end up activating what's called a glycoprotein 1b. So I activate a glycoprotein 1b on my thrombocyte. And you saw from the hemostasis video what happens at that point. The thrombocyte releases ADP, activates the arachidonic pathway, releases thromboxane A2. Thromboxane A2 upregulates the glycoprotein 2b3a receptors. They cross-link with fibrinogen, and all of a sudden, I've formed platelet plugs all throughout my system. Those platelet plugs, that formation has actually activated the coagulation cascade. So all through my system, I'm getting thrombus that are forming along there, activating coagulation, and I'm going into disseminated intravascular coagulation along the system. And so these clots are starting to form thromboemboli and travel throughout the body. Well, let's back up just for a minute. Let's see what we're going to do to treat this. So if we've got acute inflammation, no worries. If it's gone systemic, the big worry is our precipitous drop in blood pressure. Our blood pressure is dropping once again because this is not happening locally. This is happening systemically. So how are we going to address that? Well, we're going to address it two ways. One is we're going to have to give vasopressors. And so with vasopressors, what we're doing is we're going to stimulate these alpha-1 receptors. So you might end up taking a patient and putting them on Levophed, this norepinephrine drip. And the norepinephrine drip, you can also use dobutamine or dopamine, is going to plug into this alpha-1 receptors, and it's going to cause vasoconstriction. So I'm trying to push back against this, okay? But I've already lost a lot of my oncotic pressures. So another thing I might consider is colloidal IVs, or I might give albumin, because once I've caused the vasoconstriction, it doesn't help much if my oncotic pressure is out here. So what I want to do is maybe get something like albumin, which pulls fluid back inside, because I'm trying to correct this blood pressure. All right, so that's your overview of acute inflammation, and then also what happens when that acute inflammation goes into a systemic response. All right.